we talked about synthesizing carboxylic acids from carboxylic acid derivatives. And I said that I would explain the reactivity of the different carboxylic acid derivatives. So to summarize, the most reactive carboxylic acid derivative that you'll commonly come up with is the acid chloride that you'll commonly come across. And that's more reactive than the hydride, in turn is more reactive than the ester. Which is significantly more reactive than the amide. And we'll just show acetate here. So I'm working with the acetyl derivatives. This is the ethyl ester of acetic acid, the amide of acetic acid, acetic anhydride, and this is acetyl chloride. And way down on the end, if you're in base, is the carboxylic acid itself. Because under basic conditions, the first thing that happens is deprotonation of the carboxylic acid to generate the carboxylate ion. And once you already have an anionic material, it's not going to be very reactive with another anion. So when we say that the carboxylic acid is the least reactive of the derivatives in this sequence, we're not really talking about the carboxylic acid. We're really talking about the carboxylate ion. Under acidic conditions, the carboxylic acid can be more reactive than the amide. So to understand why this order of reactivity is observed, we need to think about the mechanism of the reaction. The standard mechanism of nucleophilic acyl substitution under basic conditions where the nucleophile is attacking the carbonyl group prior to any protonation of carbonyl. So as an example, let's just take methoxide ion, CH3O- as our nucleophile. Often in methanol solvent, and we would usually generate this by simply taking methanol and adding sodium metal, the other product, the hydrogen gas. And so it's a simple redox reaction to generate the sodium alkoxide in the presence of the alcohol. So what's the mechanism of this reaction? Treating the acetyl chloride as the example, first step will be to attack carbon-carbon. To generate since the leaving group is going to be a negatively charged ion and the nucleophile is also negatively charged, there's just one step, which is the loss of leaving. Which is an ester. So it just introduces ester synthesis. The acid chloride can react with an alkoxide ion to generate an ester. In fact, the acid chloride is reactive enough that the alkoxide would not be required. It could react with just methanol. We need a third proton transfer step if it were reacting with methanol. But we don't need to consider that proton transfer step, which is rapid, when we're considering the effect on the rate of the reaction of changing the group that's attached from the halide to, in this case, acetate, to ethoxide, to the amide ion, and then to NO minus. So let's consider the rate of step 2 first. And that rate is going to be controlled by the stability of the leaving group. In this case, the leaving group is chloride. And the better the leaving group, the faster step 2 should be. The more stable the leaving group, the better. That's actually common to the SN2 reaction as well, right? The SN2 reaction proceeds most readily with things that are the most stable anion. So we already know how to look at that. The stability of the leaving group follows the trend. The chloride is a better leaving group than the acetate, which is a better leaving group than the ethoxide ion, which is a better group than NH2 minus, which is a much better group than O2 minus. Which is not leaving, right? You're not going to take off an oxide ion, O2 minus, in an aqueous solution or an alcoholic solution to the base. So we know that chloride is a better leaving group than acetate, and acetate is a better leaving group than oxide. And we can know that by simply looking at the strength of the conjugate acid in each case. And we know that HCl is a stronger acid than acetic acid. Acid is a stronger acid, quite a bit stronger than ethanol. And ethanol is a much stronger acid than ammonia. And obviously, they're all much stronger acids than hydroxide. The pK of HCl, remember, -8. pK of acetic acid, approximately 5. pK of ethanol, approximately 15. Ammonia, about 35. We didn't even tell you what the pK of hydroxide was because it's a base. It's not going to behave as an acid. So if we know the pKa value of the conjugate acid from our leaving group stability tracks with acid strength. The stronger acid, the better the leaving group. So we can explain the reactivity of the different derivatives by looking at leaving group ability. So that's the rate of step 2. And step 2 could be expected to be the rate determining step when you have really poor leaving groups, like alkoxide ions or amide ions. Probably when you have a really good leaving group, though, like chloride or acetate, step 1 is likely to be the rate determining step. So what affects the rate of step 1? Since in this case the base is the same, it's methoxide in all cases, the rate of step 1 is going to be dependent on the amount of partial positive charge on the carbonyl carbon. We know that there's a minor resonance form for this. It has a full positive charge on the carbon. And a negative charge on the oxygen. The more positive charge there is here, the more likely our nucleophile is to want to attack it. What we haven't done, because we haven't really been working with carboxylic derivatives, we've been working with carbonyl derivatives, is we haven't shown the other important resonance contributor, which can occur when the atom attached to the carbonyl group actually has a lone pair of electrons. And that's the resonance structure that looks like this. The greater the contribution of that resonance structure, the more stable the carbonyl carbon and the smaller partial positive. Greater contribution of that resonance structure reduces the delta plus on carbon, and that makes the carboxylic acid derivative less reactive. Since we know that the rate of step 1 is affected by the amount of partial positive charge on the carbon, the more partial positive charge on the carbon, the more reactive, and the less contribution this resonance structure makes, the more partial positive we're going to have. So we can look at that minor resonance structure in each case. And we can surmise that the resonance contributor with the double bond to chlorine makes less of a contribution to the resonance hybrid than the oxygen in the case of the anhydride or the ester, and less of a contribution to the nitrogen. Nitrogen is less electronegative than oxygen. So it has a great ability to stabilize that positive charge. There's a slight complicating factor, though, which is that the acid chloride is more reactive than the anhydride or the ester. But oxygen is more electronegative than chlorine. Chlorine is actually closer in electronegativity to nitrogen. Nitrogen having an electronegativity, actually it's right in the middle. Nitrogen having an electronegativity of 3, and oxygen having an electronegativity of 3.4, and chlorine about 3.2. So we would predict, if it was just the electronegativity of the atom, that the acid chloride would be less reactive than it in fact is. There are in fact 2 factors that we have to think about in step 1. One is the electronegativity of the attacked atom. Because we know that there's going to be a dipole and uneven sharing of that pair of electrons. And the larger this dipole is, or the greater the difference in electronegativity, the more partial positive there will be on the carbon. This is an inductive effect. The second factor that we have to consider is the extent of overlap in the pi bond. This is the resonance effect. Because when you're talking about resonance effect, it's always pi electrons interchanging with both pairs. And orbitals of similar size overlap better. What you're looking at here is you're looking at a row 3 element trying to form a pi bond with a row 2 element. So there's a mismatch in orbital size. We have a carbon 2p orbital trying to interact with a chlorine 3p orbital. And they're going to interact constructively. But since the carbon, or the chlorine 3p orbital, has a lot more electron density up here, where it can overlap effectively, it's not going to overlap as effectively as 2p on carbon would interact with another 2p orbital on oxygen, or on nitrogen. So there's poor orbital overlap when you have elements from different rows. Which is another way of saying p orbitals with different principal quantum numbers. So an n equals 2 p orbital and an n equals 3 p orbital, like we have in the carbon-chlorine bond, doesn't overlap very well. We don't get a lot of this resonance contribution. less than you would predict based on the inductive electronegativity, the inductive effect from electronegativity, that says that chlorine is intermediate in electronegativity between oxygen and nitrogen. You just don't get as much contribution. Even though chlorine is better at stabilizing the positive charge than oxygen, the orbital overlap is more. And that turns out to be the more important factor. And that's actually not uncommon, where the resonance effect is usually more important than the inductive effect whenever we're talking about a competition between those two effects. So we might predict that a thioester, right, if we change this oxygen to sulfur, a thioester would have considerably lower reactivity, or considerably greater reactivity rather than an oxygen ester, because the contribution to this resonance structure with the 3p orbital from sulfur would also be lower. We would predict that an acid fluoride, an acyl fluoride, where chlorine is being replaced with fluorine, might be, in fact, less reactive than an acid chloride, even though fluorine is a more electronegative element, so inductively it should be pulling more of the electron density away and contributing a lot of partial positive charge to the carbon. It's better able to donate a lone pair to form the resonance structure, so there'd be a greater importance of this resonance structure. And this resonance structure really stabilizes the positive charge of the carbon. Fortunately, the things that reduce the rate of step 1, which is core orbital overlap and a not so electronegative element that's able to stabilize the positive charge in that minor resonance structure, correlate with the things that affect the rate of step 2, which is leading movability. Chloride has the worst orbital overlap, which increases the rate of step 1, and it's also the best leader group, which increases the rate of step 2. The nitrogen has the best orbital overlap, which reduces the rate of step 1, and it's also the worst leader group, which reduces the rate of step 2. So the only factor that is somewhat counterintuitive is the electronegativity effect in the sigma bond, where the most electronegative element is not always the most reactive acid derivative, because you might have a better resonance contribution because of better orbital overlap. That orbital overlap argument ought to be somewhat familiar, because last year in general chemistry, we probably talked about the difference between CO2, which is a molecular gas, and SiO2, which is a covalent network solid. We have bridging silicons, each silicon having 4 oxygens attached to the tetrahedral arrangement. And oxygens forming. And in fact, probably talked about silicate ions. Where you can in fact make Si2O6 or minus with 2 tetrahedral silicons and 2 bridging oxygens with 4 oxygens. The difference is 3p orbitals don't overlap very well and therefore don't form pi bonds. Here we have a 2p orbital overlapping with a 2p orbital to form a nice pi bond. Here we have a 3p orbital and a 2p orbital not overlapping to form pi bonds. There are no silicon-oxygen pi bonds. And that completely changes the composition of a molecule that looks like it has the same formula. CO2, SiO2, they're both a group 4A element combined with a pair of oxygens. One's a molecular gas and the other one's a covalent network solid. You might also have talked about how 3p orbitals in general don't form very stable pi bonds, and that's why sulfur exists as S8 solid, whereas oxygen exists as O2 gas with pi bond. Again, a molecular gas versus a molecular solid with only single bonds. 3p orbitals don't form pi bond correctly. There are, of course, exceptions to that, right? We know that the sulfur-oxygen bond in sulfuric acid so the oxygens that aren't bearing the hydrogen are shorter and stronger than the ones in the oxygen bearing the hydrogen, and that's because of the contribution of the sulfur-oxygen double bond, to some extent with pi overlap. But in general, pi bonds only form readily between 2p orbitals interacting with other 2p orbitals. So you've already seen it. You may not have explained it in those terms in general chemistry, but the same thing that results in silicon dioxide being a covalent network solid and sulfur being a crown-shaped S8 with only single bonds informs our discussion of why the acid chloride is the most reactive acid derivative. And you should be able to put any other acid derivative, bioesters, acid bromides, acid fluorides, acyl cyanides, in the scheme by considering the effect of the leader group and the effect of the pi overlap